This is a video about one of the boldest dreams in science. A single rule, a single equation, a single principle that explains everything, from the way stars collapse into black holes to the way atoms cling together to form life, from the smallest particles to the largest structures in the cosmos, all of it described by one elegant framework. It's the idea of a theory of everything. For more than a century, physicists have hunted it down.
Curious about how the world really works? Not the myths, not the shortcuts, the real science behind everything we see and experience. On this channel, we explore mind-bending physics, unravel the secrets of the universe, and uncover the hidden patterns that shape our reality. If that excites you, subscribe for weekly deep dives into science and discovery. Hit like and share with friends. Your curiosity drives our next adventure. Leave a comment and let us know what puzzles we should solve together.
They've chipped away at mysteries, unified forces that once seemed utterly different, and found astonishing hints that the universe may in fact be built on a single, deep principle. It sounds spooky, almost mystical, but it's real science, born from the struggles of Newton and Einstein, sharpened by quantum mechanics, and now carried forward by string theory, loop quantum gravity, and other radical ideas. And the truth is, we may be closer to this ultimate theory than most people realize. But before we dive into the cutting edge, let's start with the question, what do we even mean by a theory of everything? What a theory of everything actually means, and the historical path. So, what exactly is a theory of everything? Well, the phrase doesn't mean a theory that explains why you missed the bus this morning, or why cats insist on sitting in boxes that are clearly too small for them. It doesn't predict your mood, your career choices, or who's going to win the next World Cup. Instead, it's about the fundamental laws of physics, the bedrock, the rules that govern matter, energy, space, and time themselves. A theory of everything would unify all the known forces of nature into a single framework, not just describing how things behave in certain contexts, but revealing why they have to behave that way, why the universe could not have been otherwise. Think of it this way. Right now, physics is like a patchwork quilt. Some patches are incredibly precise, others are breathtakingly beautiful, but they don't all line up. If you zoom in to the smallest scales, subatomic particles, you need the language of quantum mechanics. If you zoom out to the largest scales, stars, galaxies, black holes, you need Einstein's general relativity. Both theories work spectacularly well in their own domains, and yet they don't mesh. That clash is the heart of the problem. But this idea of unifying laws, of stitching different forces into one fabric, has a long history. In fact, the dream of a theory of everything is almost as old as science itself. Let's rewind. In the late 1600s, Isaac Newton dropped a mathematical bombshell on the world. With his law of universal gravitation, he showed that the same invisible force pulling apples to the ground was also pulling the moon around the Earth and the planets around the sun. For the first time in history, the heavens and the earth were explained by the same law. That was unification. It was the first glimpse that the universe wasn't a random assortment of unrelated rules. It was one coherent system. Fast forward to the 19th century. Enter James Clerk Maxwell. At that time, electricity and magnetism seemed like separate phenomena. Sparks from a battery, a compass needle twitching north, lightning splitting the sky. But Maxwell brought them together. In a set of 4 elegant equations, he showed they were just two sides of the same coin, electromagnetism. And as a bonus, his equations predicted something no one had seen before, electromagnetic waves traveling through empty space. We now call them radio waves, microwaves, visible light. Maxwell revealed that light itself was electromagnetic in nature, another stunning unification. And then, in the early 20th century, along came Albert Einstein. His theory of special relativity tied together space and time into a four-dimensional fabric, space-time. Then his theory of general relativity went further, showing that gravity wasn't a force pulling things at a distance, as Newton imagined, but rather the warping of space-time itself. Mass tells space how to curve, and curved space tells mass how to move. It was not just unification, it was reimagination. But Einstein didn't stop there. For the last 3 decades of his life, he pursued what he called a unified field theory. He wanted to merge gravity with electromagnetism into one grand framework. He failed, but his obsession planted a seed that modern physicists are still chasing. And today the problem is even bigger, because we now know that electromagnetism and the so-called weak nuclear force responsible for radioactive decay can actually be unified. In the 1970s, experiments confirmed this idea. They are part of a single force called the electroweak force. And there's good reason to believe that the strong nuclear force, which holds protons and neutrons together inside atoms, could also merge with them under extremely high energies. So you can see the pattern. Over centuries, physics has been a story of unification. First, the heavens and earth, then electricity and magnetism, then space and time, then forces of particles. At each step, we've discovered that what seemed like separate rules were actually one. And this raises the tantalizing question, could there be a final unification, a single principle, underlying gravity, electromagnetism, the strong force, the weak force, everything? That's the theory of everything.
The clash between relativity and quantum mechanics. So, if history has shown us one thing, it's that unification works. Whenever scientists have managed to bring two forces or ideas under one roof, it's unlocked deeper truths about the universe. But now, we've hit a wall. The problem comes down to two of the most successful theories ever created: general relativity and quantum mechanics. Let's look at them separately first. General relativity is Einstein's masterpiece. It describes the universe on the grandest scales: the dance of galaxies, the crushing collapse of stars into black holes, the expansion of the cosmos itself. The equations of relativity are smooth, elegant, geometric. They treat space-time as a continuous fabric that bends and curves under the influence of matter and energy. And the predictions match observations with stunning accuracy. GPS satellites, for example, literally wouldn't work without relativistic corrections. That's how real this theory is. On the other side, we have quantum mechanics. This is the physics of the very small, the bizarre probabilistic world of subatomic particles. It tells us how electrons orbit nuclei, how photons behave like both waves and particles, how energy comes in discrete packets called quanta. Quantum mechanics is weird, counterintuitive, even unsettling. But it's also the most precisely tested framework in all of science. Quantum electrodynamics, for example, predicts the magnetic moment of the electron with accuracy to more than a dozen decimal places. Nothing else in science comes close. Individually, both theories are triumphs. Together, they're like oil and water. Here's the issue. Relativity says space-time is continuous, smooth, infinitely divisible. Quantum mechanics says that everything, energy, matter, even fields, comes in discrete chunks with inherent uncertainty. If you try to apply quantum rules to space-time itself, relativity breaks down. If you try to apply relativity to the quantum world, quantum mechanics breaks down. It's like trying to fit two puzzle pieces together that almost, but not quite line up. Take black holes as an example. Relativity predicts them beautifully. Regions where space-time curves so steeply that nothing, not even light, can escape. But then, you bring in quantum mechanics, and suddenly, black holes aren't stable at all. They emit radiation, slowly evaporating over time. This is called Hawking radiation. And here's the kicker. Relativity says information swallowed by a black hole is lost forever. Quantum mechanics says Information can never be destroyed. So which is it? Both can't be right. This is known as the black hole information paradox, and it's one of the sharpest battlefields between the two theories. Another clash happens at the Big Bang. Relativity describes a universe expanding from an initial singularity, a point of infinite density and curvature. But quantum mechanics refuses to allow infinities. It demands uncertainty, fluctuations, probabilities. When you try to calculate both at once, the math explodes. You get nonsensical infinities everywhere. Physicists call this incompatibility the greatest unresolved problem in science. And the quest for a theorized everything is in essence the quest to reconcile relativity and quantum mechanics into one framework, a quantum theory of gravity. To get a feel for how hard this is, imagine two languages. Relativity speaks the smooth, poetic language of geometry, curves, surfaces, continuous flows. Quantum mechanics speaks the jagged, staccato language of probabilities, random jumps, discrete states, uncertainty. Both languages describe reality perfectly, but in different domains. And when you try to translate directly from one to the other, the meaning gets scrambled. So far, we've only been able to patch things together. The standard model of particle physics, for example, brilliantly describes 3 of the 4 fundamental forces: electromagnetism, the weak force, and the strong force. It's a quantum field theory, and it works. But it deliberately leaves out gravity, because gravity refuses to play nicely in this quantum sandbox. And yet, we can't just ignore gravity. It's weak compared to the other forces, but it dominates the large-scale structure of the universe. You can't explain galaxies, stars, or even the flow of time without it. So any genuine theory of everything has to include it. This is why physicists sometimes say relativity and quantum mechanics are both right, but not right together. We have 2 incomplete halves of a larger truth. The big question is, what is that larger truth? The bold attempts at unification. So if the problem is that relativity and quantum mechanics can't be glued together, what are the possible solutions? Well, physicists have spent nearly a century trying, and in that time, a handful of daring ideas have emerged, ideas that might just point the way to a theory of everything. Let's start with the most famous contender, string theory. The idea first appeared in the late 1960s, almost by accident. At that time, physicists were trying to understand the strong nuclear force, the one that binds quarks together inside protons and neutrons. Early calculations suggested that instead of treating particles as point-like dots, you could treat them as tiny, vibrating strings. The math worked surprisingly well. And then, something even surprising happened. When researchers examined the theory closely, they found that it naturally included a particle with the exact properties of the graviton, the hypothetical quantum particle of gravity. It wasn't put there on purpose, it just fell out of the equations. That was a huge clue. From that point, string theory shifted focus. Maybe it wasn't just a theory of the strong force. Maybe it was a candidate for a quantum theory of gravity. Maybe even the theory of everything.
Here's how it works. Instead of thinking of the fundamental building blocks of reality as point particles, like little billiard balls, you imagine them as one-dimensional strings. These strings can vibrate in different modes, and each vibrational pattern corresponds to a different particle. A string vibrating one way is an electron, another way is a photon, another way is a graviton. In this picture, all particles and all forces are just manifestations of the same underlying object, the string. It's a breathtakingly elegant idea, but it comes with a catch. For the math to be consistent, string theory requires extra dimensions of space. Not 3, not 4, but 10 or even 11. These dimensions are thought to be curled up at scales so tiny that we can't see them. Like the surface of a drinking straw looks like a one-dimensional line from far away, but up close, you see it has a circular thickness. This may sound bizarre, but it's not impossible. And string theory has delivered some profound insights into how gravity might emerge from quantum rules. In fact, one of its offshoots, the ADS-CFT correspondence, suggests that gravity in a higher dimensional space could be equivalent to a quantum field theory without gravity in a lower dimensional space. In other words, space-time and gravity might be holographic, emerging from quantum information on a boundary. That's wild. But here's the problem. As of now, string theory hasn't made testable predictions that experiments can confirm. It's mathematically rich, but physically slippery. Critics argue it might be more of a mathematical framework than a true scientific theory, at least until we can prove it experimentally. Still, string theory isn't the only game in town. Another approach is called loop quantum gravity. Instead of strings, this theory tries to quantize space-time directly. Remember, relativity treats space-time as a smooth fabric. Loop quantum gravity says, what if that fabric is actually woven from tiny discrete loops, like a kind of quantum chainmail? In this picture, space-time itself has atoms, fundamental chunks. They're unimaginably small, far below the scale of particles. But if this is true, it would mean that space and time aren't continuous at all. They're granular. Just as matter is made of atoms, space itself would be made of atoms of space. This approach has led to some fascinating predictions. For example, it suggests that singularities, like those inside black holes or at the Big Bang, might not exist. Instead of infinite density, the equations show a kind of bounce, where collapsing matter rebounds, avoiding infinities. That could resolve some of the contradictions between relativity and quantum mechanics. There are also hybrid ideas, attempts to merge concepts from both string theory and loop quantum gravity. Plus newer, radical approaches, like the idea that the universe itself emerges from quantum entanglement, that the fundamental stuff of the universe isn't particles or strings, but information. One of the most mind-bending proposals is that the universe might be like a quantum computer, and the geometry of space is nothing more than the web of relationships between entangled bits. In this view, the geometry we experience is just a shadow of deeper informational rules. All of these attempts are, in their own ways, glimpses of what a theory of everything might look like. But here's the catch. None of them have been decisively proven, not yet. Experiments at the Large Hadron Collider have found the Higgs boson, confirming part of the standard model, but they haven't uncovered new physics that string theory, supersymmetry, or other ideas predicted. Cosmic observations give us hints, like dark matter and dark energy, that don't fit neatly into current models. But no candidate theory has yet passed the ultimate test, making bold predictions that match reality. So are we stuck? Not quite, because the story isn't just about elegant math or perfect experiments. It's also about the direction physics seems to be pointing us to. And when you look at the big picture, it seems that all roads, whether through strings, loops, or information, are all leading to one breathtaking conclusion, that space, time, matter, and energy may all be manifestations of a single, unified principle. So where does that leave us? Right now, physics is like a jigsaw puzzle with the corners filled in, but a huge piece missing in the middle. Relativity explains the cosmic dance of galaxies. Quantum mechanics explains the jittery world of particles. Both work, both are true, but they refuse to click together. And yet we're never closer. String theory, loop quantum gravity, the holographic principle. Each is a window into what might lie beyond. Each offers a glimpse of how gravity and quantum mechanics could be part of the same story. Maybe the final answer is already hiding in our equations, waiting for the right perspective. Maybe it will come from a new experiment, a fresh breakthrough, or an idea so radical that it will make Einstein's relativity look tame. We don't know yet, but history shows us something remarkable.
Every time we thought the universe was made of separate rules, it turned out to be one. So maybe, just maybe, the dream of a theory of everything isn't just wishful thinking. Maybe it's inevitable.